Good afternoon, everyone. Welcome to Takeo Tuesdays, commercial focus style. Brett Zerba here. Fairbanks is on. Hey, Paul, how you doing, buddy? A couple of hand raises to make sure you can hear me. A couple, anyways. One, two. Anybody? Thank you, Alim. I appreciate that. So today's topic is pump selections and curves and project builder. So we got a lot to cover. Rich Medeiros will be the main presenter today. I will be monitoring the questions and keeping track of all you folks, making sure you're all behaving, which I'm sure you will. But please ask some questions and we'll get through this. Takeo, 105-year-old privately held company, currently led by Johnny White, the third generation. His son, Ben White, is mid 30s, and he's involved in the company. And now there's 3 grandchildren that Johnny has that aren't quite old enough to be involved in the company. They're all less than 5, but you never know. You never know. But I'm sure I'll be riding off into sunset well before that. So we got a lot to cover today, and I will be monitoring the questions. And I do appreciate any questions that come up. We'll try to answer them. And if we don't, we'll get back to you, offline to make sure we cover all the questions. We just had a nice group in last week, and I see one or a couple of people that came to visit us last week for Takeo, for our some of our Takeo University classes. If you're ever interested in coming to the factory in Cranston, Rhode Island, and we should be able to fit in our welded products division in Fall River, Mass. Get a hold of your Takeo rep, and maybe they can sponsor you, and we can teach you in person, and even show you a good time. There's a lot to learn about the city of Providence, as well as where Takeo's world headquarters are, located in Cranston, Rhode Island. Cheryl Merchant is our global CEO currently, and her and her staff are going through an enormous amount of changes. Wait, the staff's not changing, but the company is. We are growing. We spent over $25 million in expansions last year. Our welded products division in Fall River, Mass. went through an enormous expansion. We doubled the capacity of our stainless steel foundry in Vietnam. We built another building for one of our facilities in Europe. And then we opened up two, count them, 2 vertical turbine facilities, one in Lubbock, Texas, and one in Fresno, California. So we are, it's amazing. We're approaching almost 2,000 employees worldwide. The plant in Cranston's actually working 3 shifts now. And I know a couple, I know at least one gentleman was at our facility that's on today's call. And I'm sure he was amazed at how many products, pumps and tanks were staging to be shipped out. We can't keep up. So thank you for all of that, for anyone involved with that. So let's, I think I'm done talking. Again, I'll be monitoring the questions, ask away, but I'm going to turn it over to my good friend and co-worker, Rich Medeiros, so he can lead the way. Take it away, Rich.
Well, thanks, Brett. Do we have any questions yet? Or, oh, wait a minute, it's too early.
No questions yet.
No questions yet. All right, so we're going to talk a little bit about pump selection and NPSH, which stands for net positive suction head. So let's go through the pump selection. Well, let's touch a little bit on the agenda. It's short and sweet, but it's an in-depth topic. So let's see what happens here. So we're going to start by selecting a commercial pump, how to read a pump curve, NPSH, and then have a discussion. So let's go into a little system diagram here. I've got a little system diagram, and this little guy has, should I write it down, Brett? Let me write my famous words, not for construction.
I'm taking a picture of it, and I'm getting it quoted as is.
Construction.
No temperature probes, no not enough shut-off valves, you name it.
Anyway, yeah, these diagrams are set up for classroom discussion, and they're not really intended to be copied to be used for construction. So we always have to make that disclaimer. So we have a very simple diagram here. On the the chiller, let me kind of point to the chiller in the center here. To the right of the chiller is the piping for the condenser water system, and to the left is the piping for the chilled water system. And we're interested in making a pump selection for this little guy right here. Not including the little MPV, multi-purpose valve. So let me just I'll block that out for now because I'm just interested in the pump. And you can see that it says 1190, 96.6 gallons per minute at 60.7 feet. So the actual pump selection I'm going to make will be based on 1,200 gallons per minute and 70 feet. So we're going to jump out of the presentation software and jump right into our selection software. So let's see what happens here when we go over to the website. So as you can see in the top here, if you just type in takeoutcomfort.com, you'll wind up with our home page. And we have a couple of buttons up here in the right-hand corner, upper right-hand corner. And the one we want to click on is Visit Site. We could go directly to the selection tools, but I kind of want to show you what the site looks like a little bit. And there's all kinds of information here. But for today's discussion, we're going to click on this little tab here that says Selection Tools. And then we're going to go over here to what's called Project Builder 2.0, which is our latest selection software. And it takes a few seconds for that to load. And while that's loading, we're going to click on this little tab over here that says Select Equipment, and then Pumps. Just to make sure, by the way, that I don't have any leftover information, I'm going to log out. Let me do that for a second. And then I'm going to sign back in again. Since I'm already registered and I have an account here, it shows my email address and the password blocked out. So I'm going to sign in. And when I do that, it's going to go to my input page. But first, it's going to ask me what do I want to select. So I want to select the pump. So we get the input page. So follow along, and I'll bring you through this step by step. So I think we said our pump was 1,200 gallons per minute, so I'll put that in there under the flow. I'm going to leave the units at US gallons per minute, and the head, I believe we said, was 70 feet. And for today, oh boy, that doesn't work. Sorry about that, everyone. I thought I'd shut my phone off already. So what we're going to do is scroll down a little bit here on the right and look for KS pumps. That's what I kind of like today. So I'm going to do this little check on the box here.
You know what I like, a little detail I like about this selection is it shows you a picture of the type of pump right next to the designation. You know, that's a neat visual, if you know what I mean.
Yeah.
Because not everybody knows right off the bat the model designations, I guess. So anyways.
So yeah, I picked a KS pump, which, as Brett mentioned, here's a little picture, and that's our designation for the vertical inline. So I'm going to click on search in the upper right-hand corner, and the computer is going to be pretty fast today. I was playing with it a little bit earlier this morning, and it'll show several selections. So here are all the different selections that will meet that criteria. Turns out there's 2 pages of them. So it's 10 per page, so we got 11 to choose from. Now, before we actually make a selection, if you'll notice this, the one over here on the left that has left top, it has a little triangle with an exclamation point in it. And that's to tell us that that is known as a near miss. So if I hover over the thumbnail, and then I hover over the little triangle sign, the warning sign, says rated head above maximum impeller diameter. So the ones with the little triangle exclamation point, it's like a traffic sign, a warning sign. I may not want to look at those in any detail. So if you'll notice in the top of the screen, it says hide near misses, because those are near misses. It's defined as a near miss. which means it just barely misses the design operating point. So if I click on hide near misses, you'll see those guys with the triangles go away. And how many do we have now? 1, 2, 3, 4, 5, 6, 7. So we've got 7 to choose from. Now, one of the things I like to do is I like to hover. If you'll notice, I've got my cursor floating around the screen here, and I'm going to hover over the first little thumbnail, and I'm going to get a picture of the pump curve and the system curve. And the pump selection software has placed the selection right in the middle of the green area, and I'll go over that in a minute. And so as I draw my cursor down, you can see in each pump selection, it's in a slightly different location. So here's one that's a little bit too far to the right, and that's not a good selection. This next one is a little bit far to the left, and the final one is really quite far to the left. So the thumbnails give you an indication of what the curve would look like. It doesn't show a lot of detail. So we're going to pick the one at the top of the list. I'm going to click KS8013D. D is in David. Well, let's see what happens when we click on that. We should get a nice pump curve to look at. Whoa, how's that, Brett?
Nice.
So I have a lot of things I want to cover here, but I want to make sure. I'm going to hold on 1 second, Brett. I have to clear my throat a little bit. Sorry about that, folks.
No problem.
All right, let me try this. Should have got a bottle of water. Anyway, so here's the pump curve, and we have all kinds of information that's available on the pump curve. The blue line represents the actual pump curve. The software has selected an impeller diameter of 13.1 inches in order to perform at the design operating point that we want, which in this case is 1,200 gallons per minute at 70 feet. By the way, if you notice when I move the cursor back and forth, you can see a vertical line, a black vertical line moving with the same position as the cursor. So I'm going to do my best to make the black vertical line sit right on top of the design operating point. Let's see what happens when I do that. Oh, let's see. Does that work? Yeah, it does. I'm not sure what's going to happen when I put my little pen here to work. Oh, it doesn't work with this. So we'll just stay on this for a minute. So if you notice, as I move the cursor back and forth, by the way, if you notice, see my cursor right now, it shows you the GPM and the head are changing. So if I move to the design operating point, 1,200 gallons per minute, I'm going to as close as I can. If you notice, it says 1,201 US GPM at 70 feet. Can you see that okay, Brett?
Yep.
I'm hoping everyone else can see that. So if you'll notice also, and I'm going to repeat this in a minute, but the vertical line also intersects the graph that's above the pump curve, and that's called the NPSHR graph. And if you notice, that's 1,201 US gallons per minute at 9.8 feet. So that tells us what the NPSH, net positive suction head, required by the pump. That's how you get that information. Okay. Since we've made that initial selection, let's point out a few other things that we're looking at on the screen. If you notice this green area in here, it's called the preferred operating region. And that preferred operating region is defined by the Hydraulic Institute in their performance standards. To the left of that, we call the white area between the green area and this dotted line on the left. The dotted line on the left is the minimum continuous stable flow line. And the dotted line on the right, which it looks red to me, and the one on the left looks kind of orange. Anyway, between the green line and the red dotted line, that's the acceptable operating region. And the same thing if we think of the green, where the green little box ends, and the one way on the left here, which is the minimum continuous stable flow. So you can operate anywhere in those regions, but you try to pick your pumps so that it's in the green zone area. And also the other thing you want to make sure of is that when you make your pump selection, it's nice to have a little bit of extra capacity in if you had to change out the impeller in the future. So in this case, this is a 13.1 inch diameter impeller, and I think it goes up to a maximum of 13.5. Looks like it's cut off a little bit. I'm going to try changing the size of the screen here and see if I can read it better. No, look at that. Kind of cuts it off there. Well, that's a little bit unexpected. So well, the other thing we can do is we can add right now the horsepower lines. See these dotted black lines? This shows the motor horsepower. So the one on the lowest part of the screen here, this is 10 motor horsepower. And then there's another one in there, which is 15, and then 20, 25, and 30. And the maximum motor horsepower that we can put on this pump is a 40 horsepower motor. So our design operating point is just touching that dotted black line at 25 horsepower. So I'm kind of using the graph here to see what that horsepower might be. I'm kind of looking where the arrow is. But I can get more accurate information by moving on the right here where it says power ISO lines. Click on that down arrow and then put in rated curve only. It takes a few seconds for it to update. Now you can say I have a horsepower line down here. Now when I put my cursor on the tip of the design operating point, try to get it as close as possible here. See who that's pretty good. Hey, Brett.
You nailed it.
I nailed it that time. And you can see that on the horsepower line, it says 1,200 gallons, US gallons per minute, and it intersects the horsepower line at 25 horsepower. So my visual guess was pretty good, but now I have much more accurate information. That's kind of cool, huh?
I like it.
I like it. There's a few other lines on the pump curve that's important for us to know. If I follow my cursor as I move it to the left, and as you can see, the gallons per minute gets lower and the head gets higher. And when I get all the way to the end, as far as I can go before it disappears, I want to get as close to 0 gallons per minute as possible. Oh, look at that. I did that one good too, Brett.
Man, you're on a roll today with
I'm on a roll today. So what that tells us is that the 13.10 inch diameter impeller, that blue line just above the 12.5 green line, that blue line, when I have 0 gallons per minute, it's at 80.6 feet. That's known as the shutoff head. That means that if I close the discharge valve in the field and I run the pump at the design speed, in this case 1160 RPM, it will produce a pressure differential across the pump at no flow. So you can see we're at 0 gallons per minute. And one of the nice features about this software is that you can easily find the shutoff head, and you can use that information to verify the impeller diameter in the field. So in other words, if the pump is physically running in the field and I do a shutoff head test, I might ask the mechanical contractor to close the discharge valve and take the pressure differential across the pump. By the way, whenever I ask someone to do that, I try to have them do it in less than 10 seconds. So it's nice to have a helper. So one person shutting the valve and the other person taking pressure readings, and hopefully they can do it in less than 10 seconds. Because if the pump runs for any period of time, it will overheat and eventually destroy the pump. So that's useful information. That's called the shutoff head. These other kind of curved lines here are lines of constant efficiency. So the one that's highest on this loop here is about 85% efficient. And halfway between those two 85 numbers, maybe that's 85.5, halfway between the two. And the highest efficiency at the highest impeller diameter and the design speed is known as the best efficiency point, or BEP. So the letters BEP stand for best efficiency point. Before I continue on, Brett, do we have any other questions that people?
Yeah, so you semi-answered the one of them. How do you find the best efficiency point? I think the nomenclature tells you it too, doesn't it, or not? Maybe not.
No, that's one of the things that the it doesn't actually publish the best efficiency point in words, but we know how to find it. We know
Yep.
that the efficiency is the highest. And in this case, we have the 85 and 85, and we know that the highest or best efficiency point is roughly halfway between those two.
Yep.
So maybe that's roughly 85.5 efficiency.
So this question came up just as you started, and I'll let you answer it. Why did you choose the KS, or what were you basing the choice of pump on?
Oh, so in this particular case, because I'm doing a classroom, it's more of just a personal preference. I just kind of like what they look like. But if I was doing an actual design, I would look at 4 characteristics. First is the performance, which is what we're looking at right now, and that's the efficiency, the GPM, the flow. And then if I'm interested in the net positive suction head required, in this case, it's 9.8 feet. That's all important information. So that's the first thing. The second thing is the amount of physical space the pump takes up. And each different style pump has a different footprint. And that's important because if someone is trying to use the least amount of real estate, they might select one pump over another. The third category is maintenance. So in that case, um, the pump that I selected is called a KS, which is a split coupled pump, which means that you can service the mechanical seal without physically removing the electric motor. And that might be important to someone. If we went with a close coupled vertical inline, they'd have to physically take the electric motor off the pump assembly in order to service the mechanical seal. So maintenance is important. And the last, which is kind of interesting, is personal preference. Sometimes customers like one style of pump over another. So those are the 4 criteria that you would use in terms of selecting your pump. And hopefully that answers that question.
I'm sure it does. So, um, how do you find the minimum flow rate that the pump can run without fail? You kind of touched on that.
Yeah, so if you can see my cursor arrow, it says minimum continuous stable flow. That's the orange dotted line. So on the left side of the screen here, this shows you what the minimum flow would be. So in my case, the blue line represents the pump curve, where the pump curve intersects that orange dotted line. Kind of move it back and forth here. It's approximately 350 gallons per minute, roughly in that range. Maybe 358, 355. So that's the minimum stable flow that we would have for that pump. And then if you're interested in the maximum allowable flow, we follow the blue line down to where it intersects the red line here. And then it also displays, in this case, 1754 gallons per minute. Hopefully that answers that
Yep.
question.
Tom is making a good point, and I kind of noticed it too. But looks like the selection point is on the 12.5 inch impeller, but I think the blue is the impeller diameter is the same color as the pump curve. That's the
Yeah, so it's
differentiating. Yeah.
13.1 inches. And so I've shown everyone the graphical information, but there's also uh, text information. If I go over here on the left side of the screen, I can click on this word performance. And then when I click on the word performance, you can see I get a nice little tabulated screen here. And then for the impeller diameter, if you'll notice, the impeller diameter is 13.1 inches. So I can verify by going to this screen, and I can see the values in very precise. So if you notice before, let's click on the curve button again. And I hovered over the design operating point, try to get as close there. It said the net positive suction head required by the pump is 9.8 feet. But I can also double check that down here. If you notice on the screen, it says NPSH required 9.8 feet. So we have the data both in terms of the curve, because the curve helps us understand a little bit more about which direction things are going. In other words, if I move to the right, you can see the horsepower line increases. If I move to the left, the horsepower line decreases. So sometimes it's helpful to see the graphical representation along with the narrative data. There's another point that we're interested in. If I again follow the blue pump curve all the way to the end, you're going to see my vertical line is going to disappear in a second. And then as soon as it disappears, I'm going to go back on that again. There it is. Whoops. Try to do this here without messing it up. There it is. And the horsepower that it's reading right now is approximately 31.7 horsepower. And that is the maximum amount of horsepower that this pump would consume when connected to the electric motor. So we have a name for that. It's called the non-overloading horsepower. So if we wanted to ensure that the electric motor did not overload, we'd have to install or select this pump with a 40 horsepower motor, because the non-overloading value is 31.7, and we want to make sure that our actual horsepower selection for the motor is greater than the non-overloading horsepower. And at 31.7, again, if I go over here to the performance tab, you can actually see it. NOL, non-overloading horsepower, is 31.72. So that's the actual value.
If I was a rep or an individual, I would consider using a 30 and making sure people understood that that covers the majority of the range of that curve, but it would all be documented properly. So I wouldn't have to go up from 25 horse all the way to 40. I can only go from 25 to 30.
Yeah, because you'd be a bit, if you went with a 25 horsepower motor, you would be right on
Right.
your design operating. As soon as you went to the right of that a little bit, you would overload the motor.
Right.
You don't want to do that.
How do we see available motor voltages?
That is in the configuration software. So in other words, and I'm not going to configure the pump, in the configuration process, you get to select the actual voltage that you want for this particular motor pump combination.
And just
So
to
in other words, when you get to that level of detail, I recommend that you start working with the rep so that they can guide you through the different motor horsepower and combination selections, because it will affect the price. It'll also affect the delivery date, depending on what you pick for a motor.
are the pump horsepower, is the pump HP represent BHP or motor horsepower?
What you see on the screen here where it shows the power line, that's the pump horsepower. That's the power input to the pump shaft, sometimes referred to as the BHP or brake horsepower. Some people will use the term shaft horsepower, but the industry standard is to use the term brake horsepower.
How do you find the minimum speed to run pumps safely using VFD? That's
Well,
a
again,
loaded question, you know.
yeah, so in terms of the minimum speed, we can click, see over here on the right where it says multi-speed curves. We're going to click on that. And we're going to see a bunch of curves that have different speeds associated with it. And if you'll notice, the minimum speed here is 580 RPM. Then if we follow that curve all the way over here, you can see that the minimum flow at the minimum speed is approximately, let's see if I can read this, it's approximately 182 gallons per minute. And 580 RPM for this particular pump is 1160. And we like to be, so if that's a nominal 1200, so if I divide that by 3, that's approximately 400. So we're recommending a minimum speed in this case of 580 RPM. You could go a little bit lower because generally speaking, we like to stay above 1/3 of the speed. And we could also display the speeds not only in RPM, but if I click over here where it says motor frequency, you'll notice it changes it from RPM to Hertz. Because some people are used to thinking in terms of Hertz. So we can actually go down to approximately 20 Hertz. I'm going to change this lower value here from 29.5 to 20, which is a reasonable speed. And when we do that, we'll see a plotted line down at 20. And in this case, we can go as low as roughly 1,200, I'm sorry, 100, almost 130 gallons per minute at minimum speed.
Someone asked if can you go above 60 hertz? You need to consult the factory.
Right. You need to consult the factory, contact your rep, tell them what you would like to do and how much faster you want to overspeed the pump. And then they will get together with the engineering group that's physically located in Cranston, Rhode Island, and then they'll give you some guidance on that.
Um, and how do you maintain the highest efficiency throughout the lifespan of the pump? Good maintenance.
Well, one of the things we're going to get to in a couple of
Yeah.
minutes here, because we want to
Yep.
cognizant of time, is net positive suction head.
Yep.
And one of the things that can happen to a pump is that if you don't have enough pressure available at the suction side of the pump could potentially cavitate, which would shorten the pump's life from multiple years to just a few days to a few weeks. That's how
So,
dramatic
so
cavitation.
I just want to comment about this Project Builder 2.0. It's very difficult, and to show every feature that's available in this. I challenge folks that want to play with it some more, do it on their own. Click on it and log into our website and go right to it. It's very easy to do.
Yeah,
You know,
and our reps that are out there are very, very supportive in using the software, and with just working with it for a few times, you get pretty good at it, at least in terms of the basics. Software can do a lot of things that you may not think of when you first start using it. So that was pretty much what we wanted to cover for the selecting a pump and using the software, the selection software, and a few other odds and ends things that the software does for us. So before I switch over to the NPSH discussion, do we have any other questions out there, Brent?
we are question free right now. Oh wait, are motors for 400 volt 50 hertz also available? 380 50, I think.
You'd have to check with the reps to see what voltages are available. I don't have that information.
We do sell outside the country quite a bit, so I have a good feeling that they are, but please double check with your TACO rep.
Yeah. I mean, the standard voltages for the United States are usually a 208 volt and 460 volt. But then as you travel around the globe, you'll find different voltages. It's just interesting, all the different voltages that are out there.
Rich, we have a very, very important question, and I feel bad. I have played with Project Builder 2.0, and somehow I lost all my data. Who can I contact to help get this information back? Please make sure you register when before you use the software. You want to add to that at all, Rich? I feel bad.
Yeah, I mean, if you did register and you use the save function, it should be in there somewhere. If I don't know what to tell you, if you did not register and you did not use the save function, I honestly don't know whether you can ever get that data back. I have a feeling you cannot.
Yeah. Okay. Well, I'll take Amy's question offline and see if I can help her. Go ahead, Rich.
All right, so I'm going to jump back into the presentation software because I just want to recap the stuff that we just talked about. And so I have this little, there's the pump curve that we just looked at. Oh, this is a little bit different pump curve here. But I do have this screen. So I've labeled everything for everyone. So you can see, for example, hopefully my pen works. Let's see, does my pen work? It does, look at that.
Working good.
It's working good. You always have to make sure your pen works. But I have the design operating point called out up here in the upper left-hand corner, 1,200 gallons per minute at 70 feet. And you'll see that I have the arrow pointing to the design operating point. I show the system curve. So this is a nice little because you'll get the recording. What is the recordings available? What, 24 hours from now,
Yep.
Brett?
Yep. About 1 o'clock tomorrow afternoon.
Yeah, so this is a nice little reference slide so that you can, if you ever lose track of some of this terminology. There's the shutoff head right there, pointing to the maximum pressure at zero flow. Put that like there. There's the net positive suction head value on the top graph. There's our best efficiency point for this particular pump application. There's the pointing to the pump curve. That's the blue line on the graph here. And there's our non-overloading horsepower for this particular pump. So that gives you a nice little graphic.
Take a picture. Take a picture.
Take a picture, or when you get the presentation, you can do a screenshot and make future reference so that you'll know exactly where all this terminology comes from. Okay. So the next thing we want to talk about is how to calculate net positive suction head available. So I'm going to go back and forth between a couple of slides. So here we have a little system diagram. And the system diagram shows an open condenser water system. I'll kind of put a little bubble around that. That means that our cooling tower, shown here on the left, is open to the atmosphere. And let's assume for our discussions, we are at sea level. So we'll just make that note here for a moment. We are at sea level. And what happens is that when a pump is running, the actual pressure that's required at the pump suction flange is a value that we have to maintain in order to ensure that the pump does not cavitate. And the way we do that is to ensure that the pressure at the inlet of the eye of the impeller is above the vapor pressure. So I'm going to go back here, this is the top screen here for a moment. And so in our example system, we have a condenser water system where, let's assume the condenser water is 100 degrees Fahrenheit. We know the atmospheric pressure, and again, I'm going to underline this here, at sea level is 14.7 pounds per square inch absolute. If we multiply that by the conversion factor, which is 2.31 feet of water column per PSI. So in other words, if I multiply 14.7 times 2.31, it'll come out to approximately 33.9 feet of water column. And in this case, the A stands for absolute pressure. So I have a system that is flowing 1,400 gallons per minute. My pipe size is 8 inches. My velocity is 8.98 feet per second. So when I went in and did the selection software for the piping system, I used the HSS or HVAC solution software. Let me just go down to the diagram one more time so everybody knows what I'm talking about. So I created this diagram using the HSS software. And I believe we have on our Takeo Tuesday agenda sometime in the future. Don't we go through the HSS software, Brett, in some detail?
Yes, we are on July 15th.
Okay. So hopefully you folks will sign up for that, register for that Takeo Tuesday, and you'll be able to generate diagrams just like I have here. All right. So some of the other data, pipe size. So let me go back to the diagram here. I think it was 8 inch in this case. Oh, I didn't display the pipe diameter. That's okay. So we, generally speaking, we want to be somewhere around 8 feet per second. In this case, it's slightly over 8 feet per second, which is pretty good. The pressure drop for the pipe is 3 feet per 100 feet of straight pipe. We have elbows that have an equivalent length of 16 feet of straight pipe. Isolation valves, a pressure drop of 1 foot. Basket strainer has a pressure drop of 10 feet at 50% capacity. And the vapor pressure comes from the steam tables is 2.2 feet of water column at 100 degrees Fahrenheit. So I actually have the steam tables listed here. So here's the steam tables. And the first column for the steam tables shows the temperature in degrees Fahrenheit. And the second column shows the absolute pressure known as the vapor pressure. So we have 100-degree Fahrenheit water for our system, and it says that the vapor pressure is 0.94924 pounds per square inch absolute pressure. And we're going to convert that into feet of water column by multiplying. I'll take the 9.94924 pounds per square inch absolute, and I'm going to multiply it by times 2.31, which is feet of water column absolute divided by PSI absolute. And when I do that, it's going to come out to approximately 2.2 feet of water column absolute. And that's the vapor pressure. So we want to make sure that our pressure at the inlet of the impeller is above our vapor pressure. And so that's what I wrote down here. So before I go any farther, Brett, I've presented a lot of information. I'm going to show them the calculation for that in a second. But do we have any other questions so we don't lose anybody?
Yeah. How precise can impellers be cut to? Say an increment of every a tenth of an inch, or is it a quarter inch? I forget.
I believe it's an eighth of an inch on the diameter, which means that it is a 16th of an inch on the radius.
Okay. Fair enough.
Anything
Good.
else?
Oh, we're good.
Okay. So we got the data from the steam tables, and here's the diagram. So what we're interested in figuring out is what is the net positive suction head available for our system. And since this is an open system, the controlling pressure is our atmospheric pressure. So I'll point to that. And I want to make sure that everybody understands that in an open system, the atmospheric pressure is dictated by the elevation you are above sea level. Since we are today at sea level, our atmospheric pressure is approximately 14.7 pounds per square inch absolute, which ultimately multiplied by 2.31 is approximately 33.9 feet. Then we also have the vertical distance between the center line of the pump and the water level in the tank of the cooling tower. And we also have the friction head, which is the calculation that we're going to have to do in order to figure out what the pressure drop is as the fluid is flowing through the piping system. And then the vapor pressure. The vapor pressure is what we said before. It's that same value. Let me go back a slide or two. It's 0.94924 times 2.31, which is 2.2, and that's where that value comes from. So here are all the values, the 33.9. If you notice, the vertical distance is plus or minus. So whenever the water tank is above the center line of the pump, that's a positive value. Whenever the water level in the tank is below the center line of the pump, that's a negative value. We actually designed a system for Fall River, Brett, a few weeks ago, where we're pumping from a tank that's below the water level in order to, below the center line of the pump. But in order to make sure that the water doesn't drain out of the pump, we had to put in a check valve, which in that case is known as a foot valve. But we don't recommend you do that unless you have very special circumstances.
Someone asked if there was a minimum distance, and there really isn't, but the more the merrier.
When they say, oh, you mean in terms of the positive value?
Yeah.
Yeah.
Is there a minimum height difference?
Not so much in a minimum distance, but when you add up all these numbers, so the vertical distance is 10 feet, the pressure drop is 17.71 feet, and the vapor pressure is 2.2 feet. And when we add and subtract that and we do the arithmetic out, it comes out to approximately 23.99 feet. And in this case, the net positive suction head at 23.99 feet is greater than what's required by the pump and by approximately 3.99 feet. So we have a small safety margin of almost 4 feet. So the pump, let's just go back to our little diagram that I had for this particular thing. I think we had in this case 19.5, that's approximately 20 feet, right? Yeah, That's right to me. Yeah. So we have a surplus, if you will, of approximately 4 feet. I personally like to make sure we have at least 5 feet. So that's 4 feet. That would tell me that maybe one way of getting more pressure in the system is to elevate the cooling tower. So move it vertically upward by 1 foot. So that instead of being 10 feet, if that was 11 feet, that would be adding a foot to this. Instead of having a 4-foot margin, I would have 5-foot margin. I generally like to have at least 5 feet pressure, 5 feet greater than what's required by the pump. So that gives us a quick
Can you
snapshot.
recalculate and show where that 33.9 feet came from? The atmospheric.
Yeah, so the atmospheric pressure pushing down on the open tank. Remember, this is open to the atmosphere. So I'm pointing down that arrow. Let me get rid of all my arrows for a moment. It just gets a little cluttered here. So I've got the atmospheric pressure, and then if I'm at sea level, S-E-A-L-E-V-E-L, 1 atmosphere is equal to approximately 14.7 pounds per square inch absolute. And to convert that into feet of water column, I would simply multiply that by times 2.31, and that's the conversion, feet per PSI. When I do that multiplication, that comes out to approximately 33.9 feet. And in this equation to work, this NPSH calculation to work, the atmospheric pressure has to be in feet, and there is that value of 33.9.
Nice.
So hopefully that answered someone's
I'm,
question.
I'm sure it did. Mike said, got it. How do you calculate vapor pressure for a glycol mix?
Well, in this particular case, it's an open system. So since you're evaporating water, there would not be any glycol. As far as the vapor pressure for glycol is concerned, you'd have to go online, probably Google it. And I actually had a chart that I picked up, a nice little chart from the ASHRAE show. There was a couple of companies that was, I think Valvoline was one of them, and they were selling or promoting their propylene glycol, and they had a nice little chart which I picked up, and it shows the vapor pressure for different temperatures. So you have to do a little research, either with online probably is the simplest thing, and go to one of the chemical manufacturers. You can go to Dow Chemical, you can also go to Valvoline, and there's a bunch of others that are floating out there somewhere. And you can download a chart that'll show you the vapor pressure for a water glycol, and they give it to you for different solution concentrations.
So, is it important to consider low water level? Isn't it? It is important versus full tank. It depends where it comes out. It doesn't matter, right? The level of the water.
Yeah, the vertical distance is always measured from the center line of the pump to the water level in the tank. And if it's a variable water level in the tank, you would pick the vertical distance at the lowest water level in the tank.
So someone's asking if you were only 6 inches above MPSH R, that's too close. I mean, you need to have some. There's too many variables to be that close. You know what I mean? You're less than a
Yeah,
foot
I mean, I think
above
you're
it.
taking too much of a risk. If your calculation comes out to be, let's say you needed, again, 20 feet, that's what was required by the pump, and you had available 20.5 feet, which is 6 inches, that's not enough safety margin, in my opinion. I wouldn't take the risk. Other people
Some
might, but I
someone's
wouldn't.
challenging your 5 feet as not being enough, which is
Well,
true.
like I
You know
said,
what I mean?
5 feet for me is an absolute minimum. If I had a choice, I would like it to be higher than that.
Yeah, because that basket strainer could clog. All of a sudden, your 17 feet or almost 18 feet of pressure drop goes up to 25 or something like that, or they add 3 elbows, or it's just it's things happen. Things happen.
Yeah, I think you make an excellent point, especially as we look at this little diagram here, the basket strainer. You can see how important it is to measure the pressure differential. So you should have a pressure gauge on the suction side basket strainer, reading one pressure, and then another pressure gauge on the discharge side of the, oops, I did that backwards. Sorry, Britt. Let me erase that. So on the suction side, you might have one pressure, and on the discharge side, you'd have a lower pressure here. So you want to constantly measure this delta P across here, because if you had in your calculation, I believe we allowed 5 feet. Let's go back here and see what we did. For our basket strainer, we allowed 10 feet. There it is right there. We allowed 10 feet. So to your point, Brett, if the actual condition starts getting close to approximately 10 feet, then you know you're going to have a problem because you don't have any safety margin left. And so, you know, the basket strainers, especially in open cell cooling towers, are very popular because there's a lot of debris that can float around in the air. In some parts of the country, the debris is higher during one part of the country versus another. I was out at Oklahoma. I was in Oklahoma some time ago. It's like it was about 4 or 5 years ago, and they have the beetle season, Brett.
Oh,
They have millions and millions of beetles that fly around. I think it's around this time of year. I don't know exactly when. And it finds its way into the cooling tower and gets picked up by the basket strainer. So they have to empty the basket strainer like every other day because
man.
the thing picks up all the beetles. So, yeah, I mean, you might run several months with hardly any pressure differential because the basket strainer is not taking anything out. But if you have parts of the country that you have beetles, you also have, I have in my yard those little seeds that, like, when they fall, they spin like little helicopter blades.
Yep.
And boy, once
Someone
they
said
get into a cooling tower.
Eugene is adding to the conversation, saying cottonwood is the worst. So he must have had experience with cottonwood too.
Yeah, ask him what part of the country is cottonwood in.
I'm sure he'll respond. Someone asked, this is obviously for an open system. How does the calculation change for a closed system?
Well, in a closed system, you're not the pressure is not being controlled by the atmosphere. So the atmosphere, it becomes a controlling factor in an open system. In a closed system, let's assume that this was a closed system, and we know it's not, but we would have on the suction side of the pump an expansion tank. Let me kind of draw in the expansion tank here. Expansion tank, and then we'd have a little PRV, a fill valve, pressure regulating valve, PRV. And between the PRV and the expansion tank, they work in concert to control the pressure on the suction side of the pump. So theoretically, if you needed a little extra pressure, you could change the setting on the pressure regulating valve and also on the expansion tank to ensure that you had enough pressure so the pump didn't cavitate. So in a closed system, you get to control the pressure within certain parameters. But in an open system, it's driven by the atmosphere, and it becomes a function of elevation above sea level.
So Alaska, believe it or not, is where that gentleman was from with the cottonwood.
Cottonwood.
Yeah.
That's interesting. Yeah.
Well, Rich, me and you have a big problem. I apologize, Javier. He sent in a question, but it's in Spanish. So
No, I can't help you.
I know, neither. I can barely read English. Can you go back to your pump curve,
Yep.
or a pump curve?
Yeah, let me go back to what we had here. This is
I don't want to
one.
not answer Robbie's question. So, uh, uh, um, what is the purpose of the system curve?
Oh, that's a great question. So the system curve shows us what the relationship is between pressure drop and flow as the water flows through the system itself. So for example, I could actually have a system without a pump in it. Most people say, what is he talking about? So let me try this. Let's see, we're going to discard all of that. And I'm going to create another screen here. How are we doing for time, Brett, by the way?
6 minutes, 5 minutes.
Okay, 5 minutes and counting. It's like a blast off here. All right, so we're going to get rid of this. Get rid of that. Okay, so now I have a little screen that I can draw on. And so ask me the question one more time so I make sure I give the correct answer.
You just wanted a better understanding of what the system curve was.
Yeah, so let's assume for a moment that I had a reservoir up here in the top of a mountain somewhere. So here's a mountain. And then I have a pipe coming down. And let's say that I start my system at this point A here, and I put a pressure gauge here. All right. And let's assume that the pressure drop from my elbow and through my piping is negligible. We're just going to make that up. So as my water flows through my pipe, perhaps it comes across a valve. And the next thing it comes across is a basket strainer. And then maybe it comes across and you wouldn't put this, usually you don't put a basket strainer in line with a Y strainer, but I'm kind of exaggerating here. And maybe there's another valve over here somewhere, little valve. And then over here, I wind up with another pressure gauge. So let's assume there's no pressure drop in the vertical or the horizontal pipe, and the height difference between, and then eventually, let's say, it just flows out of the pipe. All right, so I have higher pressure here and a lower pressure here. And let's say the height of the fluid relative to the center line of my pipe. I'm going to kind of draw this, and I'm making this number up, by the way. Let's say that height difference was 50 feet. And the pressure drop from my first point A to point B, that is a delta P equal to 50 feet at, I'm just going to make up a number now. This is just make believe, but at, let's say, 100 gallons per minute. So between connection A and connection B, I'm measuring a pressure differential of 50 feet, and that is the height of the fluid that I have. So what I'm really saying is that the system curve, I can draw the system curve here. Let's assume that I had 100 gallons per minute on my x-axis and 50 feet on my y-axis. And where those 2 points intersect, I would have a nice smooth curve that looked like this. It's a quadratic curve, goes through that point. And that shows me the characteristics of my system curve. Ta-da!
Nice.
Isn't that cute?
It is.
And
Good
there's no
explanation.
There's no pump. So the system curve is a function of the piping and the components that are in the system. They're not dependent on the pump. In this case, I have a reservoir where I can have enough pressure to push the water between point A and point B. And that represents the system curve.
Awesome.
Any other questions?
No, we're question free.
Question free? Oh
I
my
know.
golly.
We had a couple people's excellent presentation. Well done. Nice. Getting some good feedback already, Rich. You know, you Tanner, we just got rid of the guy and he's back giving us nice compliments already.
Hey, Hugh, how you doing? How was your trip back? He was in Rhode Island the other day with us.
Enjoyable as always, John said. I know. Please share presentation file. We'll most of it, there really weren't a lot of slides, but we will, anyone that asks for it, if you send an email, we'll send it out to your questions. So you guys are well. We will talk. Travel was tough going home. Oh boy.
Oh boy.
Oh boy. Well, that's not good. That's not good. Not good. Anyways, Rich, you want to say goodbye before
I am going to say thank you so much for listening to us go on and on about pump curves, pump selection, project builder, and net positive suction head, NPSH.
All right. So, Jimmy, or anyone else on the call, if you go to our website and go under training, you can sign up for, let's see, I think we're in the third quarter. We in the third quarter or second quarter, Rich? I don't know what quarters we're in.
The second quarter. January,
second,
February, March, April, May, June.
April, May, June. I think
Right.
we just published the third quarter ones. So anyways, on our website is where you have the ability to sign up for future Taco Tuesdays, both residential and commercial ones. So that's where they are available. And our next one scheduled for June 3rd is HVAC hydronic balancing. This was originally scheduled for April 22nd, but it had to be moved. So it is on June 3rd, HVAC hydronic balancing.
Is that when you stand on top of a building with a cup of water and you try to balance yourself?
That's what you do.
Oh,
But
wow.
don't do that from
Don't
here.
do that.
Don't do that. All right. Yeah, someone said don't forget about Taco After Dark. Well, the guy talking right now is so old that he can't do Taco After Dark because after dark that's when I'm sleeping. Anyways, but there are some. What email do I address my request for PDH certificates to? You should be able to respond right to the email that you signed up for, Richard. But if you have an issue, you can email me and I'll try to track it down for you. BREZER at TacoComfort.com, all one word. Again, BREZER at Taco, TACO, Comfort, COMFORT.com. And I'll
So
try to track
Brett,
them
now
down.
that your email is out there for
Yeah,
thousands of people, they're going to be sending you requests for things like walking their dog and
nice.
yeah, that'd be
I
cool.
gotta send money, send money, send money. Anyways, thank you everybody. Rich, great job as usual, and hopefully we'll see some of you or hear from some of you in 2 weeks. So goodbye, everybody. Thanks a lot. You're welcome. You're welcome.
Thanks a lot, as they say.